happened, the thing about particle accelerators is up until now, we talk about the muon and the pion, I talk about the guy in the mountain, the guy in sea level, the way they're discovering these things is by, they weren't really telescopes, but they're cosmic rays. Stuff is coming out of the sky, and I'm sitting here measuring what comes out of the sky. So I figure out how to make detectors for these things, and then I detect the cosmic rays, whether they're coming from the sun, or from the Big Bang, or other parts of the universe, I don't care. But I have cosmic rays coming in, and I'm doing measurements on them, and I'm discovering particles that way. That means the only things I can discover is what's coming out of the sky, what the universe has generated, including some of these exotic particles, the pi and the muon. Exotic at that time. But now what happens when I have particle accelerators and I have the guys ready to work on it is I start making particles. And I end up with, first thing I discover is a kaon. Remember I had the pion, which was these two guys. Now I have a K, and the K decays into 2 pi's. And then I have a different kind of kaon, a charged kaon. This was a neutral kaon. And my charged kaon, and that thing is going to decay into 3 pions. And then I find something called an eta particle. And then I find phi, and I've got the lowercase omega, I've got a rho. All these particles, these are all mesons that come out. These are all made up of 2 quarks. I don't know that yet. All I know is that I'm discovering all these particles. And then on the baryon side, these are the mesons, these are middleweight particles. Meson means middleweight. On the baryon side, I find this really heavy thing called a lambda, which decays into now a proton and a pi. And I've got, then I find a sigma. I find this thing which is called the xi, but everybody just calls it a cascade because you can't say xi in the middle of a sentence. Right like that. And then a delta. These are all capital Greek letters here for these things. And this, so all I know is these things are kind of heavy. These things are kind of medium weight. So I call these the mesons. I call these the baryons. I don't know anything about this stuff. What I do know is that it's kind of strange that I've been discovering so many heavy particles. It's strange that I had this K that has enough energy that it can make 2 pions out of it, because the pion was already a middleweight particle. And why did I find something now that I can make more of these middleweight particles out of? It's very heavy. It's strange that this thing is heavy enough that I can get a pion and a proton out of it. There's a little oddity to this. There's something else that is strange, is that these things live so long. They live for a longer time than you would expect. You would expect if they're that heavy, they'd fall apart quickly, but they don't. It takes a while to decay. 1,000 times longer. The analogy, it's only 1,000 times longer. So instead of being 10 to the minus 15th seconds, they live for 10 to the minus 12th seconds, something like that. Which doesn't sound, they still sound like small times, but it's the equivalent of finding a village in the mountains of Peru where people live to be 70,000 years old. That would be fundamentally new biology. Same thing here. It's like tiny amounts of time, but it's a substantial difference.
Do they know at that point that the proton, for example, is composed of
they don't know anything.
ups and a down?
Nothing on this board is known.
Okay.
All they know is they've got these particles that come, and that these are kind of strange. And so, we have charge. We knew about charge, plus and minus charge. We know about some degree of spin. We know a few of these properties. Something has mass. So we said, well, some of these particles are strange, so we'll assign them a property called strangeness. So this thing has 1 unit of strangeness, and some things have maybe 2 units of strangeness. And that strangeness is both they're too heavy and they take too long to decay. And we're just going to call it that. So we start sorting these things out. Some are strange, some are not strange. There's a hint over here where we're going. So this number of particles keeps exploding, and we get a quote from the, this is the one thing worth reading today. This is from the Nobel Prize acceptance speech in 1955, which is right in the middle of all this stuff. There we go. Okay, so this is Willis Lamb, begins his Nobel Prize acceptance speech in 1955. When the Nobel Prizes were first awarded in 1901, physicists knew something of just 2 objects, which are now called elementary particles, the electron and the proton. A deluge of other elementary particles appeared after 1930. The neutron, the neutrino, the muon, which in those days we called the mu meson, the pion, which is those first 2 that I showed from the cosmic particles, heavier mesons, which are these, and various hyperons, which is what these things were called in those days. I've heard it said that, quote, the finder of a new elementary particle used to be awarded a Nobel Prize, But such a discovery now ought to be punished by a $10,000 fine. So we have this mess. Nobody has any idea what is going on. It's a zoo, it's total chaos. And, you know, we don't know what's happening. And that's 1960. I don't know if there's a coincidence that the 60s were total chaos or yes, but that's the way it was. In the mid-60s, Jomon got a Nobel Prize. Well, he got the Nobel Prize in '69 for working in the mid-60s for figuring out that there's a pattern to this. It wasn't quite this pattern. It was something called the Eightfold Way. And it turned out that if you assumed there were things inside, something like quarks, if I can call them quarks, and the word quark was a joke in the first part. It came from Finnegan's Wake, James Joyce. It was 3 quarks for Mr. Mark. They needed quarks, they needed something, he called it a quark. So these things are quarks. When they figured out that protons had to be made of something, they didn't call them quarks, they called them partons, up until the mid-80s, because nobody would associate the quarks with the partons. The quarks were just a bookkeeping device. They were something you just put in because you had to. It made these nice patterns work out right. So he came up with these quarks, and at the time, it wasn't all of them, and figured out by looking at the quarks, there should be another particle there somewhere. There should be, and he called it an omega. I should have this thing. So, and it should weigh this much. So go look for it. This was in 1964. So they went, they looked for it, they found it. It was exactly where it was supposed to be. It weighed what it should weigh. He told them where it was, and they found it. And when his use of these quarks to figure out what the pattern should be worked, and was able to predict a new particle, all of this fell into place. And the zoo essentially collapsed into a regularly ordered structure of how you can put quarks together in order to make particles. And so that was the story essentially of the 60s. So the problem with the quark, we talked about before, now we talk about the quark having color, and you can't have a quark by itself. That is upsetting. The fact that, okay, I'm going to have this particle. I promise this particle is in there. I'm going to call it an up, whatever it is. But you can't see it. You can't take it out. You can't have it by itself. You can only have it together. I can have things that are made out of quarks, but I can't have quarks by themselves. And that is an unpleasant thing. No one likes it. And there's another thing that no one likes about the quarks, which is that I have this, these quarks have to be fermions. Right? They're spin 1/2, which means I can't have them all in the same place. So how am I going to get these 3 quarks in the same place? And the answer is, I'm going to add color. So this is where the strong force gets its color from. This is where it starts from. It doesn't start because I need the strong force, I need a new kind of charge that has 3 different flavors, 3 different colors, 3 different kinds. It starts because I need to be able to get 3 quarks all together, and I can't do that. Because these guys are going to have the same spin, they're going to have all the same characteristics. These are identical, and I can't put 2 identical fermions in the same place. So I need some way to make them not identical, and so that's color. I'll say, okay, this one's green, this one's red, this one I don't care, it could be red, well, it's got to be blue at this point. But if this one's green and this one's red, then they have something different about them, and they're not identical, so I can put them in the same place, because they're not really the same thing. And that's how we get around this fermion problem, by introducing color, which is also kind of a funny way to do it. This is around 64 again. But still, this is my bookkeeping device, but what's inside a proton? A proton is full of partons. I've got 3 partons inside my proton. And I know I have partons, so here's my proton. I know I have these 3 partons, because if I smash it hard enough, it flies into 3 pieces. So it must be made of 3 things. These are my 3 partons, and I'm going to go ahead with my physics with this and do my experiments over with partons, while you guys pretend there's this thing called quarks. We'll just pretend they're quarks, we know they're not really there. And this is sort of a problem. It's also a problem because at this point in the story, what we have, I talked about these ones over here that were strange, we assigned strangeness to them. Part of what Jomon did, where he gets this Nobel Prize in the 60s, with the quark bundles, he's got the strange quark. He says, what gives something strangeness is if it has a strange quark. And the reason that it's heavier is because the strange quark is going to be heavier than the up and down quarks. The other reason is that the strange quark can only decay into an up or a down quark here from the weak process, from the weak force. And that weak force is much slower than the strong force because it's weaker. And that's why it lives longer, because I have to wait for the weak force. I can't just go through the faster strong force. So that strangeness is now explained. So now I have a problem, because in this picture, I don't have these guys anymore. These guys haven't been discovered yet. But I had the muons from the cosmic rays. So I had the electron neutrino, I've got the muon, I've got the muon neutrino. I've got the up and the down, and now I've got the strange that explains those strange particles that have strangeness. I got 4 of these, and I got 3 of these, and I don't like that. That's unpleasant. So I keep looking and say, there ought to be something. So I have in 74, let's see, let me go up here. Where is it? Burton Richter, over here, says there should be something else. I want something else here. And it would be charming if there were something else, because now it won't work. So now I'm going to have myself a charm quark. And it's the charm is the fact that now it's going to match. And so I'm going to have this charm quark, and I got to go look for it. And this is where someone asked about the theorists. How many of these guys are theorists? How many experimentalists? This is where the experimental piece comes in. So I need charm. I'm going to make something which is made up of 2 charm quarks. So I've got a meson, down C bar, 2 charm quarks. Go find it. Goes, finds it. It's found twice. One on the East Coast, one on the West Coast. On the West Coast, we have Richter, who finds this thing and calls it the psi particle, which is written like this. On the East Coast, we have Sam Ting, who also finds it, and he calls it the J particle. They find it at the same time. Ting actually finds it just a tiny bit earlier, goes out, is meeting with Richter on the West Coast, and they realize they've actually got the same particle, and so they publish it together. So whether it's called, for a while it was called the J psi or the psi J, and it depended which coast you were on. It was kind of like the East Coast, West Coast wrapper dual thing. So this is the J psi, is what it's called. Now the other problem with naming it the J, remember I said you're not allowed to name things after yourself? In Chinese, Ting is written like this. So, nobody knows, but Ting invents a particle, or discovers a particle, names it the J, and that's great. So some people don't like it for that reason as well. But the J psi is the name that's stuck, and that's the name that we typically use for this. Now there are additional excited states of this particle that are kind of like bigger, the same number of quarks, but they have more energy. Talked about before. Those are just called the psi with the mass in parentheses afterward. And the reason for that is that Ting only found the ground state, the first level J psi particle, and the higher states were found out in California. So that's, this is 1974. Now, there's a problem with that, which is that so far I've only found something that had 2 charm particles, 2 charm quarks. I want to have other particles that are going to be a charm, maybe a charm with the down or a charm with the strange, some other combination of these things, so that I can have other kinds of particles. And so those are discovered. That's called naked or bare charm. So because I can't see the charm in here. If I look, the charm and the anti-charm cancel out. So from a distance away, it doesn't look like it's charmed at all. So I want to find a particle that has, let's say, something like that. And that would let me see charm from a distance. So this would be, but the charm is exposed, so it's naked or bare. So that, everything looks happy until I'm in the mid-70s, I'm in 74. Then in 1975, a year later, the whole thing is ruined. Somebody finds a tau. Really, really heavy electron. These are basically just heavier kinds of electrons, otherwise the same as electrons. So that ruins it. Until, so I'm going to need something else here. And this is where Leon Letterman comes in and saves us with the oops Leon, which becomes the Upsilon. This is, he's got himself a new quark, which is the monarch, which at the time was more popular to be called beauty. It was up, down, charm, strange, truth, beauty. And for most of the time, because these quarks weren't really real, they were just bookkeeping devices and nobody wanted to believe them, even though they were increasingly useful, the names were silly on purpose. So we have the truth and the beauty. We don't have truth at this point, although it becomes postulated you must have truth because now I've got a real imbalance. I know if I've got a tau, I'm going to have a tau neutrino. I also know that it's going to be really hard to find. So we just believe that's there, not worry about it. Eventually we can find it. We have the bottom here from the upsilon. Again, this is 1981. And then remember with the charm, it's not good enough to just find one that has two bottom quarks, or two beauty quarks. I need to find one that has one beauty quark and one something else so I can see this naked charge or this bare charge, which would be either naked beauty, if we use that term, or if you like the bottom term, bare bottom. So that's what we're looking for at that point. So in 1983, we find naked beauty, bare bottom. Fine. We're still uncomfortable with the bare bottom. So then the other thing we find in 1983, this is all talking about the quarks. We still don't have force carriers for this. We have the weak force, which I haven't got to yet, but we don't have any way for these forces to be transmitted. We have a photon that we know for E and M, but for the other forces, we don't know what's going on. We don't have gluon, we don't have W and Z. So also in 1983, we discovered, these are called vector bosons. That's when we discover these other pieces here. This side, we're able to find the W and the Z because we have accelerators that are big enough, and detectors that are sophisticated enough to be able to sort them out from everything else. And now we have a way for the weak force to operate. And again, 1983. In 1987, the particle physics book I used as an undergrad was published, not long before I was as an undergrad. So we have the strong force. We have these basic particles. I know that I need some kind of gluons to mediate these things. The book still refuses to refer to quarks as what's inside the proton. Those are still partons. And there's a statement in the book that I just found the other day that no one would say that the evidence for gluons is compelling. This is in 1987. And this is now a fundamental piece of everything that we have now, everything that we understand. So I'm going to stop here and think about this for a minute. 83, 87, we still don't have the whole picture together. Think of what it's like to come of age in a field like this when starting in really the 50s, 60s we still knew nothing. It was a total zoo. It was in 74 that we start with, 64 to 74, we start with getting the first semblance of order here. 74 to 83 is when we fill in this puzzle. I can't have my placemat here in 1982 because me as a child, the age of my kids, I can't have this placemat because these things haven't even been discovered yet. They haven't even been postulated yet to a large extent. I still only had 2 generations of quarks here. So we're living in this time when all of this stuff is being discovered, being sorted out, and to a large extent being solved very quickly in an orderly fashion that works and has tremendous predictive power. And I can say, there's got to be another particle here, and here's where it is, the accelerators go and they find it. And that's the story time and again with each of these things. This book, my phone book of particles, is populated by particles that you sit here, you write down, you say, there must be a particle there, let's go find it, and then you find it, you put it in this book. That's what these accelerators are doing, that's the search for all this stuff, is looking for things that, by this point, you know are supposed to be there, and that's just a story, it's not just, okay, it's obvious, who cares, that's the predictive power of the standard model. So coming of age in a time like this it's like being in the crew of the HMSB. This is like if you were sitting in the room during the Constitutional Convention, when the US Constitution was being written, and people were figuring these things out in the first time. It's kind of like being at the, right after the destruction of the Second Temple, when Rabbinic Judaism was taking form. When I had this old version, the temple Jewish stuff, and now I have Rabbinic Judaism which comes up, and we've got to figure out how to do all this without the temple and everything changes like that. And there's a whole new structure. It's like being present for that, being, coming of age, being in the field in that time of that 60s, 70s, 80s, is really watching all of this happen. And you're not just watching it happen. It's not like you have an Einstein or you have Darwin or somebody who is a great genius who's able to figure this out. You have a collection of people, and there's a constant interplay back and forth between them. And you can go to the conferences, and you can see them argue with each other. And you can, you read the articles, and it's all happening as you're there. You're in the middle of all of this stuff. And it's not just stuff. This is what the universe is made out of. This is the fundamental constituent particles of the universe. Everything there is made up of all of this. And it doesn't get any smaller, it doesn't get any more basic. And that's why, it's why two things. That's why people of my generation, a little bit older, a little bit younger, are motivated to go into this and study this work. That's why I'm teaching this class. That's what this is really all about, is knowing you're in the middle of all this. That's also why this stuff is in newspaper articles all the time. That's why we spent nearly the cost of one single B-2 bomber to try to build the superconducting super collider in Texas. That's why we have the Large Hadron Collider in Geneva in Switzerland, part of France there. And we're spending billions of dollars on these things. That's why we're talking about, what is the search for the Higgs, the search for the next thing. Why at this stage are we putting this money into it? Why is this stuff sexy? Yeah, it's fundamental. But it's sexy because this is the period in which all this is emerging. It's really within all of our lifetimes that this is happening. Tamara.
So what is your dissertation about?
Mike.
As you were going through this coming of age during this time of growth and change, what is your dissertation about?
What did I do?
Yes.
I started out with, as a small child, 5, 6 years old, seeing that there was constituents of matter, and thinking that there's a way to understand what everything is made out of. That's what I'm going to do with my life. So I was about 5 years old when I decided I wanted to be a nuclear physicist. At the time I meant particle physicist, but there wasn't much of particle physics at that time. Later in high school or junior high, I figured out there was particle physics, and that's what I wanted to do. What ultimately happened is this stuff became so popular and so sexy and so hard to do to get to these very heavy, very hard to find things. The top quark wasn't found until sometime, I think, grad school at the time it was found. Is that 95? 95. We found the top quark. So I was in grad school at the time. It takes hundreds of people to do these experiments, and it takes years to build them and run them. And so when I was in grad school, I looked at what there was, and I said, let me do nuclear physics, because I can answer some of the same questions. But instead I have experiments that I can build myself, and then I have a team of between 5 and 10 people that are working on it. I can do the whole thing over the course of 6 months instead of 6 to 8 years. And so I can get some of the same stuff. I can still take the particle physics classes, but do a lot more hands-on work with it. My wife, Susie, took a different path, stayed with particle physics, and worked on these kaons that I had talked about before. The first strange particles. The first particles involved a strange quark. And the way they decay, there is a special thing that I'll tease you with now. It said matter and antimatter are the same. Right? They're just more or less mirror images of one another. And one thing that happens with matter and antimatter, because they're the same, if they come together, they annihilate one another. And they just go into energy. So the way I can draw that is as 2 electrons. Let's have my electron, and I have a positron. They come together, they disappear, they turn into a photon, pure energy. Okay? This is matter-antimatter annihilation. I can do the opposite, I can create them. If I have pure energy, I can make a pair of matter-antimatter things. So the universe starts, everything is balanced, there's no difference between matter and antimatter. So everything I make, eventually, will find its partner and annihilate and turn into pure energy. So the universe should be, based on the standard model, a soup of just energy. Everything should have annihilated. Everything that gets created should be destroyed almost immediately, because I'm going to make matter and antimatter in equal proportions. It turns out that there's a violation of that symmetry between matter and antimatter that happens really only with the kaons. There's one other particle that's quite a bit heavier. It's called B's. It's not this B. It's capital B. It's a big fat kaon. These 2 kinds of particles are the only particles where this happens that we know of, where there's an asymmetry between matter and antimatter, where it doesn't behave the same way. And that asymmetry is what is responsible for the fact that we have matter in the universe and not nothing in the universe. We could have, it could be antimatter, it's the same, it doesn't matter which one you say is matter, which one you say is antimatter. But the fact there's an imbalance between matter and antimatter is a result of a broken symmetry, an unevenness in the way everything behaves, specifically in the kaon system, in these strange particles. So Susie's dissertation, which is the unasked answer to your question, her work was on the decays of the neutral kaons into these pions. and to study what that asymmetry was and figure out why we're all here in the first place. So she got to the more fundamental stuff. That was with a medium, well, for particle physics experiment, small, it was kind of 150-ish physicists working on it. It's still one experiment, years of analyzing the data that we'll get to in the future. Any last question before we wrap up?
Was there anything else like particular about the 80s that made these things possible in terms of technology? In other words, could you have done all this on a blackboard with chalk, or did you need more sophisticated computers as they started to be developed, or more sophisticated microscopes?
Computers become really important as you get into the 90s, late 80s into the 90s, because you have to be able to, when you do the experiments, the early experiments you do them, you can actually look at a photograph of bubbles in some hydrogen and see what the tracks were.
Mm-hmm.
It gets to the point where to find these harder to find things, you have to do it zillions and zillions of times. And in those days, you had actually rooms full of women who were just trained to look at photographs and look for certain patterns. And they would just look at these things. That's one of the things actually, as an undergrad, you do as a lab, is look through the films and calculate some of these decays just by looking at that. At some point, you need computers to do that because the signals are very small and the amount of data you need is enormous. You also need to be able to build these gigantic machines to do it. But other than that, which is very recent, you didn't need computers for this stuff, but you did need to do the experiments. You needed the accelerators, and the accelerators had to get to high enough energy to make these things. If I can't make the particles, I can't study how they decay. If I predict a particle is there, I can't go look for it unless I can get to high enough energy. The high enough energy needs a bigger machine to do it, which when we talk about accelerators, probably next week, we'll get into that. And that's really what sets the pace of these things. There is more speculative physics. I mean, right now there's people with chalk that run off with all the string theory stuff, and they're so far ahead, nobody's ever going to build an accelerator to get to those energies, so to some of us that's less relevant. But that's really what drives it.
Did you also need advances in the mathematics to get some of this done?
The development of the math was kind of along the development of the physics. It's not so much new developments in mathematics as it is applying math that already exists to figure out which parts of it reflect the physical realities. So, group theory is there and it's been done. This is group theory in here, and you do need it, but you didn't necessarily need to develop it from scratch. So this happens to be this group and that group. So it was recognizable, people knew what was going on. That's really what drives this color story, why I can have color lists versus whatever. Okay, we'll get back to more of this next week. The things, though, that I want to leave you with is what's left. So we got to this story where we get to the mid-'80s. We're still discovering all this stuff, and we have a solid model here. It looks good. Everything fell into place. The things that are left are, at this point, in let's say 87, what is actually inside a proton? Which I showed you 3 quarks. We talked about whether it's partons. Eventually, we realized that, yeah, quarks are the way to do it. And we also realized that it's not 3 quarks. It's a big, messy soup of quarks and gluons, including some quarks that aren't even supposed to be there, but have 2 ups and a down for a proton. But here's my proton. I've got a bunch of strange and anti-strange quarks floating around there as well as tons and tons of glue. And it's that big soup. So we still have to discover this, which comes later in the 80s. The fact that the quarks and the glue are actual real things, we don't have that from this picture yet. I just talked about CP violation is that story that I just talked about there. That comes later, and of course the Higgs, where these things get their masses from. Those are the kinds of when you enter this in the 90s, mid 90s, into the 2000s, the kind of stuff that people are talking about and sorting out. So that's the history lesson. That's where I'll stop for now. We'll do next week. We will pick up with the weak force, which I kind of left and said there's this other weak force that's able to change these things. That becomes kind of an interesting story and allows us to get into as well something called Feynman diagrams. This is a Feynman diagram. And the last thing I'll say for today, I told you there would be no math in this class. Get it? Well, I lied, but you won't know. So, I know this short one. This is actually a mathematical equation. It looks like a picture of what happens. I mean, electrons come together, they make a photon. The photon turns into a couple of pions. Looks great. This is math. It's just another way of writing an equation. So there's a tremendous amount of math here. It's tremendously powerful. It changed our ability to do these things. A lot of what it did is it made it possible for guys like me to be able to solve the mathematical equations of what goes on here and predict particles, which is something, if I had to do the actual math itself, way beyond what I thought I So we'll talk a little bit about how that comes about. Again, the weak story, which is beta decay, which is all kinds of things that happen, and actually drives